All right. Yeah. Hi, everyone. I'm now recording a video for the probability and statistics class on Thursday. It'd be done on Thursday, but I couldn't attend because of other meetings. I'm recording the uh, lecture here, and yeah, you can see this uh, while in class, maybe. All right, so um, I will continue. Okay, let me just close my video. I will continue with the standard normal variables. So previously we have the uh, normal random variable, which has its own table. So this is the table for the normal random variable, and this is just one that I took from the textbook. You can look at other sources for the table, and they will all tell the same things. So what we need to um, pay attention to is this is for the standard normal random variable for again normal probability distribution, and if our random variable is not a standard normal one, or it's not a standard one, well, what we do is we have to convert them into a standard normal variable. So here we have the like the formula or the equation where suppose that we have the normal random variable x that is not standard. So just to remind, the standard normal variable has the mean 0 and the um, variance 1. Therefore, the standard deviation is also 1. So the standard normal variable is denoted as z. This is what we saw in the table. And we can convert this x into z by basically um, subtracting with the mean and dividing this by the standard deviation. So here z is the standard normal variable, and this is the z value obtained by standardizing x. So for example, if we have this kind of random variable with x, we can transform this into this z. So relative to the mean, in which position our desired like a measure is in the standard normal run variable. So for the normal run variable that's not standard, we have like a mean 10, and here we want to see the point 13 um, goes to which point in the standard one. Here we see that the point 13 on the value 13 here is equivalent to the value of 1.5 for the standard normal random variable. So the example here, suppose that we have the digital signal with the mean of 0 volt. Okay, so this is suppose that this is the noise. So the noise here has the mean of 0 volt, and it has the standard deviation of 0.45 volt. And here the system assumes a digital one has been transmitted when the voltage exceeds 0 0.9. And what is the probability of detecting a digital one when no signal was sent? So in other words, this signal is purely noise. All right. So the noise here has the mean of 0 and the standard deviation of 0.45. So here this is like the mean, and this is the standard deviation. And what is the probability of detecting a digital one when none was sent, right? So all of these are noise. So then what we are looking for is the probability that the noise here is more than 0.9, because the question here asks what is the probability of detecting a digital one when there is no actual signal. In other words, there is only noise, and the noise here has to be more than 0.9, because the requirement that the system assumes a digital one is that the voltage exceeds 0.9. Therefore, here we look at n more than 0.9, which is equivalent to like a z more than like a 0.9 with mean 0. So this is 0, and it's divided by 0.45, and this would be 2. So problem of finding the probability of the noise more than 0.9 is equivalent to finding the probability that the standard normal random variable is more than 2. And by looking at the table, we get like this 0.02275. So the way we look at this is that, okay, so again, probability that z is more than 2 is just 1 minus probability of z less than 2. Okay, so this is what we get from the table, and we just subtract this from 1 to get 0.02275. So we again can look at this table. For z more than 2, what we look for is, I think, this. And we get 0.02275. All right, so that's about normal distribution for the continuous random variable. Now the next distribution that we look into is the binomial distribution, which is actually for discrete random variable. So binomial distribution here is closely related to the what we call the Bernoulli trial. So this is the trial, or let's say the experiment, where there are only two possible outcomes. So let's say 1 and 0. And a random experiment here that consists of n Bernoulli trials will have this characteristics. So first, the trials are independent. Also, second, each trial results in only two possible outcomes, labeled as success and failure. And then the probability of success in each trial, denoted as P, they actually remain constant. So yeah, this is one example of this is, let's say, the coin toss, where you have only two possible outcomes, which is the success and the failure. And the probability of getting success and failure in each trial is the same, right? As long as the coin is not broken or something. And each trials are supposed to be, or each trial here is supposed to be independent. So this is an experiment, like again, coin toss, or other like a yes no trials, which results in either yes or no. So the binomial distribution here for the discrete random variable is following this equation. So the random variable x that equals the number of trials that result in a success has a binomial graph variable with parameters 0 less than p less than 1, so p is the probability, then probability mass function of x, large X, of the random variable x is written as this. It's n choose x, so this is just a combination between n and x, times the probability p to the power of x times 1 minus p to the power of n minus x, where n here is the like the total number of trials that we have. So this is just like a little bit more explanation for the combinatorial. So it's the total number of different sequences of trials that contains x successes and n minus x failures. So we have only two categorization here, success and failure. So if we toss a coin and let's say the result is head, then we can say that it's a success, or we can label it with a failure. It's up to us, but what we know is there is only two possible outcomes, which is success and failure. And this is the mean and the variance of the binomial distribution. So if we get like or if we look at the definition of the mean, so we have like x times fx, and here the probability of getting the um, like a one or in one trial the probability would be p. So if we perform the trial like n times, we will get like n times p. And the variance, we can follow the similar structure. So we have like a Vx. The variance are also denoted by sigma square, and here it is just p times 1 minus p plus others plus like a p times 1 minus p. So if p, let's say this is a half and this is a half, we will get more variance. So this is also a half. But if one of the sides are having a better probability than others, so let's say 0.8 and 0.2, then we will have less variance. So yeah, that's the binomial distributions, the mean and the variance of the binomial distribution. So other example here, so let's say that each sample of water has 10% chance of containing a particular organic pollutant, and we assume that the samples are independent with regard to the presence of the pollutant, and we are asked to find the probability. Then in the next 18 samples, exactly two contain the pollutant. So here we have the number of samples or the number of trials is the same, which is like the number of total things that we do or that we take. So in this case, it is n is 18, and exactly two contain the pollutant. So in this case, this would be x. So from 18 we take 2, and the case of we get the success. In this case, the success means like containing a particular organic pollutant, which is actually not a good thing, but yeah, we define that as a success, because what we are concerned of is that the number of the pollutant, which should be 2. So in this case, this would be P. So yeah, we just basically plug in these numbers into the equation, into the formula. So here we have p x equals 2, and this is the combination between 18 and 2. So we take like 2 from 18, and the probability here is 0 0.1. Therefore, p is 0 0.1, and 1 minus p is 0 0.9. So here 0 0.1, this is p, this is like 1 minus p, and this is p power the number of success uh, that we specify, and this is the number of non-success, which is 18 minus 2, or in other word, this is the yeah, in other words, this is like the number of failures that we are concerned of. So yeah, we get like this combination, all of the combinations, and we get this success part, and this is the failure part. And once we calculate this, we will get like this value 0.284. And then probability of at least 4 samples here contain pollutant. So note that this is at least 4 samples here contain the pollutant, which means that yeah, we are looking for p of x uh, more than or equal 4, which is the combination between 18, take or choose x. So this x is from 4 to 18, which means that it's basically we just break this down to like 5 and 6 and 7 and so on until 18. Um, sorry, until 18. And actually, there is maybe shorter way where we just look at like a p x less than 4. So this should be shorter because it's like a px 0 plus px plus 1, right? Plus, no, sorry, x equals 0, px equals 1, here plus px equals 2, plus px equals 3. So this is the same, and yeah, again, because this is the probability mass function or probability distribution function, the sum should be 1. So here, this part and this part here should be the same. So, sorry. Okay, so I forgot that this is more than or equal. So we have like x equals 4, and so on. Okay, sorry, where are we? So yeah, we are looking at this probability of x more than or equal 4, which is the same as probability of 1 minus probability of x less than 4, which is equals 0, x equals 1, x equals 2, and x equals 3. And we will get the same result here. We basically just need to calculate each of these to get the sum here, or the total um, probability for this. And then probability that between 3 to 6, so between 3 to 6, here should be like a 3, 4, 5, 6. So we just sum each of this with 3, with 4, with 5, and with 6 as the x. So for example, if this is like a if x equals like 5, then it would be like 18 takes 5. This is like 0 0.1 to the power of 5, 0 0.9 here to the power of 13. So yeah, we calculate this, and if we sum this for 3, 4, 5, and 6, we will get like a 0.265. All right, so that's for the binomial distribution. And here there is like actually a relationship between the normal distribution and the binomial distribution. So the normal distribution here is often a good approximation to a discrete distribution with yeah, the shape here would look like a normal distribution. So if you um, try to plot this binomial distribution for like um, yeah, any numbers here. So actually we can see this in this example here. So it looks like the normal distribution, especially if we have the probability being in the middle. So if it's like a half, then it's good. It's like a symmetric. But if it's not half, it's like 0 0.9 and 0 0.1, then it would be not really symmetric. Here, actually, we have the result, mathematical result, that if x is binomial with mean, so the mean here is mu equals np. Okay, let me. With mean mu equals np and the variance sigma square is npq, then this may be modeled by the standard normal distribution with the z here being like x minus np divided by square root of npq. So if, for example, if the p here is like 0.5, then the mean is just the mean, and the variance is the variance that we get from the binomial distribution. So this would be x minus the mean, and this would be like the standard deviation, which is the square root of the variance. So if this is like a 0.5, say this is like a 20, then we just plug in these numbers, and also we can also get the numbers from this because q here is 1 minus p. So if you see like q, it's just basically 1 minus the probability, and we get the standard normal distribution. Is this. Yeah, we get the approximation between normal distribution and the binomial distribution. All right, so that's for the first part of the probability distribution. So we have the uniform, normal, and binomial. Then we will continue into the second part of the probability distribution, where we have other distributions such as Poisson, also the let's say the hypergeometric, the gamma, and other kind of distribution. Of course, there are so many of those. We cannot um, we cannot look at them into look at like the details one by one, but we will try to see some of the distributions that are rather or that are used quite often. So one example here is the Poisson distribution for the discrete variable. So here we begin from the Poisson experiment. So if the binomial distribution has the experiment called Bernoulli experiment for Poisson. This is the name of the person, and I think it's called poisson. It's not poison, but I don't know. I don't really speak French, so yeah, just look at the way people say this word. So yeah, Poisson, he's of course like a mathematician or a statistician at the time, and here, the Poisson experiment is the experiments that result in numerical values of the random variable x, the number of outcomes that occur during the given time interval or in a specified region. Um, and for example, a Poisson experiment can generate observations for X that represent the number of telephone calls received per hour, number of days closed in the schools, and so on. Yeah, so many things could be done by like a Poisson experiment. The main point here is that this is the number of outcomes that happened during a specific time interval. So this is the main like the main idea of this. And for the Poisson process, we basically have the Poisson process here, where given an interval, we assume that counts occur at random throughout the interval. If the interval can be partitioned into small enough length such that one, the probability of more than one count in a subinterval is zero, then probability of one count in a subinterval is the same. So this is like an even subinterval. There is no like part that has more probability than others. And three, the count in each subinterval is independent of other subintervals. Then this random experiment here is called a Poisson process. And here x, or the random variable that equals the number of counts here is called the Poisson random variable because it follows the Poisson model with parameter lambda. Lambda later is known as the mean, is positive. All right, so the technical part is here. The PMF or the probability mass function of the Poisson distribution here is like this. So we have fx, the PMF being e to the power of minus lambda times lambda to the power of x divided by x factorial. And here x is positive, and the mean of x here is mu, which is lambda, and the variance of x here is sigma square, which is also lambda. So the interesting part here is we already know the mean, or the mean is like embedded into the distribution, which is lambda. The variance of x is sigma square, which is also lambda, and Yeah, as the mean or the lambda grows larger, the shape of this distribution will become more symmetric. So you can see here if mu is zero point 0.1, then it means that it's very heavily skewed towards like the one that has like a less, I mean like a small x. But if mu is a little bit larger, then this is distributed more evenly across the small number of x. If mu is getting even larger, then this is distributed even more evenly, like with the respect of x. So yeah, just one simple example here. So let's say that during a laboratory experiment, the average number of radioactive particles passing through a counter in 1 millisecond is 4. Um, so we have like the time interval here. So it could be like years, could be days, could be seconds. Let's say like, okay, so what is the number of people that will enter this classroom in the next, let's say, 5 minutes? Yeah, we can say that, okay, it could be modeled with like a Poisson model or the Poisson uh, experiment process, and then the what's the number of motorcycle that like goes um, in like a street in front of the campus in 1 hour or so. So everything here is stated with respect to the time interval. So in this case, so we have the average number here is 4. So in 0 to 1 millisecond, so the average number of radioactive particles here is 4. So it could be like 4, 4. No, I mean the total is 4. Yeah, sorry. So like this is the average. And what is the probability that there is more than that actually, like probability that 6 particles enter the counter in a given millisecond. So in this case, this is the average. The average is 4. And here the probability that 6 particles, so this is like the x, we are going to yeah, just consider this too. So it's e to the minus lambda times lambda to the power of x times, so this is like a x factorial. Um, so we have this lambda being 4. So this is 4. Sorry, this is x. Yeah. So this is x is no, sorry, x is the one on top. So this is lambda 4 to the power of 6, and it's divided by x factorial. In other words, in this case, it's like a 6 factorial, and we can get the value of 0.1042, where we follow this PMF resulting from the Poisson distribution. So the maybe you can imagine that, okay, what happened if we have like x equals lambda, or yeah, what would be like the probability that we have actually really like a 4 um, average. So yeah, we can just plug in this number, so that would be like a 4 factorial, and here yeah would be just 4 to the power of 4. And we can compute that the result here would be like a quite high or higher than like probability of 6 that we have here. So yeah, that's just one example of the Poisson process. And here actually the Poisson distribution could be considered as a limiting form of the binomial distribution. All right, so the Poisson distribution here could be considered as the limiting form of the binomial distribution. So actually these two are related quite closely. And in this case of binomial, if n is the number of experiments, if n is quite large and p is small, then the conditions begin to simulate the continuous space or time implications of the Poisson process. And if n is actually quite large and p, on the other hand, is close to zero, then the Poisson distribution can be used to approximate binomial probabilities with mu equals lambda equals np. So the mean here could be the same. So mu, which is the mean in general, is equal to lambda, which is um, probability, the mean of the Poisson distribution, and NP is the mean of the binomial distribution. So yeah, later we will see the relationship between these two. So the next set of distributions that we have here, so we have the hyper geometric distribution, where this is similar to binomial, but here the sampling is done without replacement. So n here is the number of samples selected from n, where k is the number of success, and range of x and n minus x are no more than k and n minus k. And mean here is nk per large or capital N. So n is the um, entire sample or entire space, and here is how many samples that we get. And the variance here is sigma square is capital N, large N minus N divided by large N minus 1 times N times K per large N times 1 minus K per N. So this is for the hypergeometric distribution. So we have the mean and the variance here. All right, so this is the mean and the variance. And yeah, this is an example. So we have 40 components which are deemed unacceptable if they contain three or more defectives or broken parts. So we have 40 as the large N, and we have 3 as the large or as the small n. So this is like large N, and this is the small um, sorry, so this is not the small n, but this is the number of defectives, so we will go back to this later. And here the procedure for sampling from a lot is to select 5 components and reject if a defective is found. So if we have five, or if we take like five components, and if we find one, then we say that okay, this is rejected, and this lot or this part of the components, this part is not accepted. So what is the probability that exactly one defective is found in the sample if there are three defectives in the entire lot? So here we get like, or we look at F1, which is the combination of K X. So K is the broken one. Here it's like here, this is K, and this is X, and this is N as the entire components. K is the defective again. So small n here is from the sample we take like a 5, and uh, we suppose that those 5 are like uh, one block in one part. So there is like no difference between those 5, and we reject that if like a defective is found out of that 5 components. So then we get the combination between 3 and 1, and then between 37 and 4 divided by 40 and 5. So this is like a 0.3011, or it detects a bad lot about 30% of the time. So yeah, there is like a 30% chance that um, yeah, we get three defectives if there is one defective we take from that 5 components. So it's actually quite large, quite high probability relative to like the number of components and the number of um, like a defect, and also the number of blocks that we take. All right, so the next distribution here is a gamma distribution. All right, so here the gamma distribution is for a continuous random variable, and this is related to the Poisson process that we have previously. The gamma function itself with parameter r. So this is just a function, right? So we have the gamma r. So this is gamma here. This is gamma. And this is the integral of x to the power of r minus 1 times e to the power of minus x dx, where r is positive. So if we have, let's say, the r equals 1, then it would just be like an integral of e to the power of minus x. And the PDF of gamma random variable here is that fx is the ratio between lambda to the power of r times x to the power of r minus 1 times e to the power of minus lambda x divided by gamma of r, and the mean is r per lambda, and the variance is r per lambda square. So the reason why we study this is that because it is related to the next distribution, which is the exponential distribution. And this is the special case of distribution with r in gamma here equals 1. So here we have gamma r equals actually equals 1 because R is 1, therefore gamma here is 1 also. And the PDF of the exponential random variable is fx, which is because R is 1. So because R is 1, so we have like x to the power of 0 here, and this would be like um, e to the power of minus lambda x, and this would be like lambda times e to the power of minus x. And then we have this um, gamma 1, which is lambda e to the power of minus x. So yeah, we obtain the PDF of the exponential distribution. All right, sorry, some typo here. So it should be lambda times e to the power of minus lambda x because we have lambda x here. And the mean is 1 over lambda, and the variance is 1 over lambda square. So because we have the probability being exponential here, that's why this is called like an exponential distribution. And the other distributions we have is like a Erlang distribution. And this is more general for like standard value of R. So this R is integer instead of just any number. And this is more similar to the exponential distribution. This is also a special case of a gamma distribution with mean and the variance. It's the same. So this is one example of the exponential distribution where we use what's called the Poisson process with a mean of 25, which means that we have lambda here being 25, and the probability that there is zero event in so no log ons in the 6 minutes. So we can say that okay, this is the exponential distribution because it's like for continuous time. So 6 minutes here equals to 0.1 hour, and lambda here is 25, and we consider 6 minutes, which becomes the limit of integration. So because for exponential distribution, we have this fx equals lambda times e to the power of minus lambda x, right? So this lambda again is the one we use for the Poisson process, and we integrate this with respect to 0.1 from 0.1 to infinity, and we have the value being 0.082. So note that this is not asking how many probability that we have some log-ons in 6 minutes, but we are asking about the probability that there are no log-ons in an interval of 6 minutes. So we focus on the case of no log-ons or zero log-ons in the interval of 6 minutes. So we consider that x here is the time from the start until the first lock-on, because there is no lock-on in 6 minutes, so the first lock-ons must happen in more than 6 minutes, or this could happen for like 0.1 hour. So that's the relationship between these two. We can do this with a Poisson process also, and we will have the same result. So yeah, I think that's there is one more Weibull distribution, but I think we will continue this next week. So hopefully we now get a, good like grasp of the distributions. So there are many of those distributions, and once we get the general idea of those distributions, it shouldn't be difficult to to understand the related distributions, such as, okay, if we understand like the Poisson process and the Bernoulli trials, we shouldn't have difficulties understanding the related um, distributions of binomial and Poisson and so on. So next week we will continue. Yeah, please make sure that you work on the um, assignment. Of course, we will have assignment for next week, and also we will also have the short exercise that you can look in your My ITS classroom. So yeah, I think that's it from me. If you have questions or discussions, we can do that next week. Okay, thank you, and see you next week. All right.